Okay, apologies. Good morning, everyone. My name is Karl Hiramoto. I've been working at VirusTotal now since January of 2014, so almost 10 years now. I was super stoked when I learned that this conference was going to be here because I live here. I figured I can't miss this. So was definitely happy to come here and happy to talk later about local things or anything VT. So I'm a software engineer at VT, and I primarily work on sandboxing and also the code sign analysis and other things, mainly sandboxing. But we do sandbox like 200,000 files a day. So I maintain that. I'm the author of the Box of Apple sandbox at VT, which is a dtrace-based macOS sandbox. And in today's session, I hope to show you some ways to do some threat hunting using VT, but you could also do the same techniques in almost any platform. So how many people here do threat hunting on a regular basis? Are you familiar with Yara? Familiar with VT at all? Great. To go forward, so we're just going to do a little bit of introduction at VT, and then we're going to go into some threat hunting stuff. So most people just know VT you can go out there, scan a file, scan a URL. You might not know, we've been around since 2004, so 19 years. Our database you can search files back to then. There's 50 billion files in the database, over 1 billion sandbox reports. There's about 200,000 of our own new sandbox reports per day of our own sandboxes, plus there's external partners, which is another 200 to 500,000 per day. 2 million file scans a day, and a huge database of URLs, domains, passive DNS. Everything on VT is in general a file, a domain, a URL, or an IP address. And part of the threat hunting is connecting the dots between these different things of files, domains, IPs. So threat hunting, usually we're talking about, you start with an initial set of IOCs. Perhaps you have a detection on your environment, or you're looking at some analyst report. You have this initial thread of your IOCs, of maybe a few samples. We're going to look at find what's interesting in these samples, and then we're going to find maybe commonalities between these samples. Perhaps you have a file hash and want to know what domains or IPs it reaches out to, so you can use that as a pivot point, or perhaps a unique string and pivot on those, and then you update your IOCs and you continue doing this iterative process of building more IOCs, filtering out, and you can also use that as a technique to track certain campaigns. So you're seeing as the campaign comes in, how it evolves. You continue doing this process, evolving as the campaign goes on. Very generally, you can search with Boolean logic and/or search for ranges. So if you want to search for a range of file times or file sizes or whatever, you can go back and forth with range searches. So how do we search? We want to say maybe in English language what type of behavior is happening. So we say, I want to find macOS executables which communicate over HTTP. So we have this human language query, but then we would translate this into a VT query, which would say we want to search for type, macho binaries, the DMG images, or the PKG images, and on the behavior network tag over HTTP. This is the behavior network searches in the sandbox data or the network traffic data of how it communicates. Another example would be searching, I want to search a macho, which also communicates to this known URL path. You could do that with the behavior network as well. Third example here would be, say you want to search for phishing. Maybe this is your first stage one of an attack. You want to search for maybe someone sending fake invoices, which have later stages. So this would be maybe search for name invoice with macros, more than 5 AV detections, and submitter in the US. The same technique can be worked, for example, if you want to search for someone in Ukraine, searching for Ukrainian phishings, you could use some Ukrainian keywords and submitter in Ukrainian country codes. So there's 50 different search modifiers. I don't want to go through all of them, but here are some popular ones. So the first one would be like P plus 3 is 3 plus is 3 or more AV detections, file type of machos, with an ARM CPU type compiler. Example number 2 is doing string searches within a content of the file. So content modifier searches string content, or you could use binary searches patterns as well. You put in hexadecimal numbers, and that will find a raw string within the last year of samples on VT. Third example is just we're doing macho files again with package or DMG or Mac apps. The Mac app tag is for zip files. So on a zip file, you have the macOS directory architecture that is like a .app folder. If that .app folder looks like a Mac app, it gets the tag with Mac app. And we could say with a submitter in Ukraine, an example. The fourth example would be a submitter submits an email. So there could be, we have some email submissions, and these will also be based on what submitter country we're in. And FS is the first seen, so first seen after May of this year. And you can combine all of these. So this is just going through some examples. Example number 6 is, say we want to find CVEs this year. So this is the CVE tag, CVE 2023. You can do wildcards, so you can say asterisk, or you could say a specific CVE number. However, this does depend on, there's some type of detection rule which detects it and tags as CVE. So this could be an AV detection, or it could be a IDS rule, or a MITRE attack signature, or many different ways, but it eventually has to have some type of detection which will mark it as a CVE for the CVE tag to work well there. The 7th example is this attachment. And the 8th example is searching based on file name, and you could search on ranges. So this is a range search on one single day in 2023, just like from midnight to midnight. So let's go into a real-world example here. Recently, AT&T Alien Labs published this report on macOS ad load malware campaign, and this was just in August this year, I believe. And we're going to go through individual IOCs in this report and see how we can find similar files, how this campaign is still ongoing. So in the original report, we have this HTTP post request, and we see the path, the /a/rep. And in VT or in your own environment, you could probably search network logs and search this /a/rep. And right away, we get 500 hits in the database, and many of them, I screenshotted this a couple days ago, so we have things even from this week, and we still have a lot of AV detection coverage there. And so once we have that previous 500 hits, one thing I like to do is go into the tools menu. In the tools menu, we can calculate commonality. So of these 500 files, what do these 500 files have in common? On the right-hand side, we have the domain names. So you see this pattern here. All of these files in this campaign have the pattern m.domainname/a/rep. And then on the right-hand side, we have the domains seen that are common between these. So in these 500 files, we still have, a dozen common domains in many of these different files, but each file tends to have a slightly different domain name or URL. So imagine we're going to click then on this validboost.com. And then in this validboost, we have these communicating files. So there's an additional 40 files which communicate with this one single domain. So from here, we can update our initial set of IOCs. We have more files again with the same campaign. In the original report, they also mentioned suricata rule. So we actually have the same suricata rule on VT. So everything that runs through the sandbox, we also capture all the network traffic, and we run all the network traffic through snort and suricata. And This particular rule you can search with crowdsourced IDS, and we get another 59 hits on the IDS data for files that are macho or macOS related file types. So also imagine you don't know anything else about infrastructure or campaigns. You could do the similar to search modifier. This is you just drop in a hash, and then we do with the static analysis tools, we know structural similarity. So so with a single hash, we have 19 hits which are structurally similar of the same file type. This is based on like fuzzy hashing of file similarity. So infrastructure matters. So a favorite part of mine of VT is the relationships tab. I often think of it as a pivot table. So you can go straight to relationships and say, how is this particular, in this case, is a file, how is this file related to other things on VT? So we directly know the URLs it's related to, and we see that this first URL has a detection, and then we also see these domains that it also reaches out to, or part of the URL, or it could be a domain that's embedded within the code, or it could be detected by, in the case of contacted domains, it's contacted in a sandbox execution. And in the case with looking at these domain here, we would see also these communicating files of where they communicate to, and then the files referring to is the domain is contained within the file because it refers to it within the file. So this is separate from ad load, but eventually mini malware, it has persistence. So if you want to search for persistence on VT, you could search for common persistence locations. Like you could say, we're going to have a plist in a startup items, or we're going to use plist buddy, or run at load. These are often common persistence mechanisms we see, and they are relatively easy to search for. So next part is on Yara. Hopefully you're familiar with Yara. So with VT with Yara, you can use retro hunts. Retro hunts search back in time, and the live hunts search forward in time. So with a live hunt, when a new file comes in, if it hits your Yara signature, you get a notification. Very generally, if you're not familiar with Yara, it's essentially a grep tool. You can search on strings. So we have a string, or we have a hex string, and we can say, if we're going to match either this text string or the hex string, we're going to trigger a detection. So what does a real Yara rule look like? This example here is from Elastic Security, and they have 6 different strings, so string 1 through 6, but if the condition is, if 5 of them match, then it's going to trigger. And since this is an open source rule from Elastic, we can use the crowdsourced IDS, or the crowdsourced Yara rule search, so we can search using this Yara rule and find another 8 detections here. Maybe you don't know about the VT import Yara, the VT library, import VT. So if you've ever seen in the static analysis on VT, or you've seen in the API some piece of data, but you're saying this piece of data is not easy to extract with creating a Yara signature, you can use the VT module to search through the data in your Yara rule. So for example, in this rule, we're saying the file type detection is a macho or PKG, and then we're saying in the VT behavior, in the sandbox execution, it's doing a base 64 decode. This is a common obfuscation technique. Will be a base 64 decode somewhere. And you could do the same thing in a VT query. You could also say behavior process. So we're saying the process is base 64 and the file is macho. And we get hits on things like the bundle or malware family. But there's also legitimate as well. But you get both with base64 decode. Here's another technique we can see with this VT Yara module using the Apple script eval. So we can also pull that down and trigger on Apple script executions within the sandbox. Now, sometimes you might think, I don't know what string to use in my Yara rule. One tool I use is VT-diff. So with VT-diff, you're going to use typically a number of files you want to match on. So you see, I loaded in this case 20 hashes of files I want to match on, and then I loaded up a bunch of false positives on the other exclusion side. And so we're going to find out which strings are common in this first set and exclude everything on the other side. So running this on this is with the add load campaign as well. Pulled out this 216 byte pattern, which I would never figure out manually. And then we could search on this pattern in VT. Note just here we have this byte pattern starts with 0B98. And then if you search this with the content search, this binary string, we directly find another 60 hashes 60 files to match, and everything that came up in this case was detected part of this campaign. And this, remember from the beginning slide, this app assistant was in the HTTP request. So to also reviewing here, we have, this is often iterative process. We're going to go through, find one piece of evidence, then go pull more evidence, and keep iterating through. And often we use this to see like how a campaign evolves and how to track how things go forward in time as the campaign goes forward. But you can also use this going backwards. If you want to go back in time and search for the first samples or earlier versions of the same campaign, you can do the same thing. So just on the community side, one way to help VT is submit more files. If you've got some type of crawler or you need API quota to submit more files, happy to accommodate that. Commenting on files, those comments are often searchable and useful to other users. And if you have other open source Yara repositories, we add those in. So with the crowdsourced Yara rule detection, you can, if you have open source Yara rules, we can add those in so they can be searched on within VT by the entire community. The same thing with Snort and Suricata rules and Sigma rules as well. And the best feedback, the best bug requests, the best bug reports come from users. So everyone here, you guys would be great for that. If you've never tried the war game and you have VT access, the war game is basically a capture the flag game type. You have to find the sample on VT. It's a CTF on using VTI. And happy hunting. I'm happy to take any questions or chat with anyone later. Thank you very much.